This is on Fermat's theorem in number theory. Now we shall prove Fermat's theorem, which is also known as Fermat's usual theorem. P is any prime. A is a number such that P cannot divide A. Then the result says A power P minus 1 is congruent to 1 mod P. The meaning of this is, when you divide A power P minus 1 by P, then the remainder is 1. The proof goes like this. Consider multiples of A. A into 1, A into 2, A into 3, A into P minus 1. See, for example, here, if prime number P is taken as 7, A is any number 9. See that 7 doesn't divide 9. 7 and 9 are relatively prime. Now you take all multiples of 9. 9 into 1, 9 into 2, 9 into 6. P minus 1 into A. First claim is that none of these two numbers is congruent modulo P. That means RA cannot be congruent to SA. We'll assume the contrary. Suppose RA is congruent to SA. What happens? Here A and P are relatively prime. Therefore, I can cancel A. We will get the result as R is congruent to S. Both R and S are lesser than P minus 1. So this congruence relation is impossible. See the example here. Take two numbers 36 and 54 among the products. Here the difference is 18. It cannot be divided by 7. So this is not possible. Likewise, any two multiples, they are incongruent. Any two multiple here, not congruent. All are not possible. That gives you the idea that these numbers A, 2A, 3A, etc., when you divide by P, they will have to leave different remainders. What are the remainders? They may be among 1, 2, 3, P minus 1. So P minus 1 multiples, they leave P minus 1 remainders. So we will combine these two. One side I will multiply all the multiples of A. Another side I will multiply all the remainders of A. And we have the congruence relation. Product of the multiples is congruent to product of the remainders. Left hand side you find A common, P minus 1 times, and remaining 1 into 2 into 3 up to P minus 1 can be written as P minus 1 factorial. Right hand side is again P minus 1 factorial. We observe P and P minus 1 factorial are relatively prime. Therefore, I can cancel both of them and I will get A power P minus 1 congruent to 1 modulo P. That is the required result. We shall see a corollary to this. Here we leave the condition P doesn't divide A. P is a prime number, A is any number. Then A power P congruent to A mod P. If P divides A, then both sides, they are multiples of P. Therefore, result holds. So A power P is congruent to 0, A is congruent to 0. Result holds. If P doesn't divide A, then A and P are relatively prime. We can apply Fermat's theorem. Then we have A power P minus 1 is congruent to 1 mod P. Using the property of congruence relation, multiplying by A both sides, we can conclude the statement. We shall see some examples and applications here. See here I will take prime number 11 and a equal to 5. According to Fermat's little theorem, 5 power 10 is congruent to 1 modulo 11. Now take 5 power 38, which can be written as 5 power 30 plus 8. 30 is written as 10 into 3. See, 5 power 10 whole power 3 into 5 power 8. That is laws of indices. 5 power 10 is congruent to 1. Therefore, I will replace 5 power 10 by 1. Then remaining is 5 power 8. That I will write 5 power 2 into 4. Here 5 power 2 into 4, 5 power 2. When you multiply you get 25. 25 is congruent to 3. 3 power 4, that is 81. Now 81 is 77 plus 4, so remainder is 4. Altogether, when you divide 5 power 38 by 11, see, without dividing we are finding the remainder is 4. So likewise, you can find many such results. These are some of the exercise problems which you can practice. Based on the Fermat's theorem, we have a lemma here. You have to be very careful while reading this. So we have two assumptions. A power p is congruent to a mod q. A mod q. This is data. A power q is congruent to a mod p. Two different prime numbers. Then we have a power pq congruent to a mod pq. The interesting part here is this pq is not a prime number. How the proof goes? We will use Fermat's theorem. In the place of a, you consider a power q. So a power q whole power p is congruent to a power q modulo p, which means a power pq is congruent to a mod p. Same thing I can also say about a power pq is congruent to a mod q also. Now I will explore the definition here. This means p will divide a power pq minus a. Same way I can prove that q also will divide a power pq minus a. Now using the properties of divisibility, when p and q are relatively prime, if p divides x, q divides x, then pq will divide x. So pq will divide a power pq minus a. In terms of congruence relation, it is the given result. We shall see one illustration here. We will show 2 power 340 is congruent to 1 mod 341. 341 is not a prime number. We note that 341 is product of two primes, 11 and 31, p and q. So here 2 power 10 is 1024, can be written as 31 into 33 plus 1. Therefore 2 power 11 can be written as 2 power 10 into 2, whereas 2 power 10 is congruent to 1 when you divide by 31. Here is a multiple of 31 and this part is the remainder. So 2 power 10 is congruent to 1. modulo 31. That is, on the whole, 2 power 11 is congruent to 2 modulo 31. Now 2 power 31, we can write it as 2 into 2 power 30. Again 2 power 10 is used here. 2 power 10 is 1 congruent to 11. So we replace 2 power 10 by 1 power 3. So we have 2 power 31 is also congruent to 2. So we have two numbers, 2 power 11, 2 power 31, both are congruent to 2 for different moduli, 31 and 11, interchanging the numbers. So P and Q. So the previous lemma gives you the result, 2 power PQ is congruent to 2 modulo PQ. That is, 2 power 341 is congruent to 2 modulo 341. We can cancel 2 here as it is relatively prime to 341. We get this result which is required. What is interesting to note is 341 is not a prime number, but it satisfies this result, Fermat's theorem. Therefore, this example is an example to show that Carnot theorem is not true. Now we shall take up one more result, very famous and interesting result by Wilson. For a prime number p minus 1 factorial is congruent to minus 1 modulo p. We take prime number p as 2 or prime number p as 3 initial cases. This can be easily verified by substituting for p here. Now we will prove for all values p greater than 3. Now choose all integers between 1 and p. 1, 2, 3, p minus 1. A may be one of them. A may be 1, A may be 2, A may be 3, or A may be p minus 1. Since A is less than p, A and p are relatively prime. GCD of A comma p is 1. We will consider congruence relation AX congruent to 1 modulo p. Here A and p GCD is 1 implies they have one solution. This is a property of congruence relation. So one incongruent solution, there is a unique solution, that is incongruent solution, which means between 1 and p minus 1 there is exactly one value A dash which will be satisfying this equation. We can write like this. Here A can be equal to A dash. When is it possible? Please take the case A equal to A dash. In that case, you get A square is congruent to 1 modulo p, which means A square minus 1 is congruent to 0 modulo p. A square minus 1 can be written as A minus 1 into A plus 1 congruent to 0 modulo p. Product of two numbers is 0 modulo p. This is possible if the number is either 0 or p. So if A minus 1 is 0, then A is congruent to 1. That is A is 1. If A plus 1 is 0, then A equal to minus 1 or A is congruent to p minus 1. Therefore, A equal to A dash is possible only when A is 1 or P minus 1. Leaving these 1 and P minus 1, we have remaining P minus 3 integers, namely 2, 3, 4, etc. P minus 2. Each one is congruent to one of them, modulo P. So we pair them A into A dash. See, for example, when you take P equal to 7, we have numbers between 1 and 6. 1, 2, 3, 4 out of 6. Up to 6. Here 1 into 1 is 1, congruent to 1 modulo 7. Similarly 6 into 6, 36 is congruent to 1 modulo 7. So these are the only two numbers whose square is congruent to 1. Now remaining 2, 3, 4, 5, we can club them into pairs. 2 into 4, 8 congruent to 1. 3 into 5, 1, 35 congruent to 1. Likewise, you take any prime P, the remaining numbers among 2, 3, P minus 2, they can be clubbed with another number. So we get P minus 3 by 2 pairs. Each pair is congruent to 1. So this whole product is a product of 1 into 1 into 1, P minus 3 by 2 times, and equal to 1 modulo. So left hand side you will find continuous numbers from 1 to P minus 2. So I can write it as P minus 2 factorial. Right hand side is 1. We will multiply P minus 1 both sides. So left hand side becomes P minus 1 factorial. Right hand side becomes P minus 1. P minus 1 is congruent to minus 1. And we get P minus 1 factorial congruent to minus 1 modulo P. That is the required statement. We shall see one more illustration for a prime number 13. Consider integers between 1 and 13, 1, 2, 3 up to 12. You leave 1 and 12, consider numbers 2 to 11. There are 10 such numbers. You can pair them into 5 pairs. How do we pair them? We pair them such a way that the product of two numbers is congruent to 1 modulo 13. So when you pair them, observe here, we will get all the 10 numbers. They are distinct and disjoint pairs. So left hand side, product of those 10 numbers into 5 pairs. Right hand side is product of 1 modulo 13. Now the remaining number is 1 and 12. So if you include 12 here, we get 12 factorial on the left hand side, and 12 is congruent to minus 1. Therefore right hand side becomes minus 1. Very important theorem in number theory. This is regarding quadratic equation, x square plus 1. Lot of applications for this. If you take a quadratic equation, x square plus 1 is congruent to 0 modulo p, where p is a prime number. We consider odd prime. We know that there is only one even prime, that is 2. We don't consider that case. Okay. When will we have a solution? That is, if and only if that odd prime p is of the type 4k plus 1, or p is congruent to 1 modulo 4. We have to observe that there are two types of odd numbers. When you divide by 4, odd numbers will leave remainder 1 or 3. So here solution comes from those odd numbers those odd primes which will leave remainder 1, which leave remainder 3 cannot be a solution. That is if and only if. We'll go through the proof here. Let us take A as a solution. Then A square plus 1 is congruent to 0, or A square is congruent to minus 1 mod P. P cannot divide A. By Fermat's theorem, A power P minus 1 is congruent to 1 modulo P. Here P cannot divide A, that is because if P divides A, then we will get 0 congruent to minus 1. So P cannot divide A. So we can apply Fermat's theorem. Now A power P minus 1. What is P? P is a odd number, odd prime. Can it be of the form 4k plus 3? Suppose P is of the type 4k plus 3. What happens? Then P minus 1 is 4k plus 3 minus 1, or it is 4k plus 2, or 2 into 2k plus 1. So we shall see this equation. A power P minus 1 congruent to 1. In the place of P minus 1, we will write 2 into 2k plus 1. So we will get 1 is congruent to minus 1. See, minus 1 power odd number is minus 1. 1 congruent to minus 1, which means P divides 2. Not possible. P is an odd prime. So this is not possible, which says that number cannot be of the type 4k plus 3. So only alternative is number should be of the type 4k plus 1. So we have seen that if there is a solution, it is a prime number of the form 4k plus 1. Now, converse part, if P is a prime number of the form 4k plus 1, can it be a solution? Yes, we will prove this. Okay. This proof is by giving the solution. Okay. When P is of the form 4k plus 1, P minus 1 is 4k, P minus 1 by 2 is 2k, which is an even number. Very important to note this. So we consider x, and we will prove x is a solution here. X is product of 1, 2, 3 up to P minus 1 by 2, a product of even number of terms. So when there are even number of terms in the product, if each number is taken by its negative term, product remains the same. So x is also equal to minus 1 into minus 2 into minus 3 up to minus of P minus 1 by 2. Now we will multiply x and x, we get x square. Right hand side we multiply 1 into 2 into 3 up to P minus 1 by 2. Then this product we will take in the reverse direction for our convenience, and I will call it as equation 1. We will convert these negative numbers into positive numbers by considering congruence relation. We have a simple congruence relation. P minus m is congruent to minus m modulo P. Please check this by taking the difference of these two numbers. Difference is P divisible by P. So the result holds. So this is true for any m. So when m is 1, you will get like this. When m is 2, you will get like this. Likewise, all the negative numbers in the above product is converted to positive numbers under congruence modulo P. So equation 1 is rewritten as x square is congruent to, see, first P minus 1 by 2 numbers as such. Then the next one we will consider positive integers in the reverse direction under congruence modulo P. Very important and interesting to note that the last number in the first product, first number in the last product, they are two consecutive integers. There is no other integer in between. Which means here in this big product, we are considering all integers from 1 to p minus 1. Which means x square is congruent to p minus 1 factorial modulo p. But we have a famous result, p minus 1 factorial is congruent to minus 1 modulo p by Wilson. So the result becomes x square is congruent to minus 1 modulo p, or x square plus 1 is congruent to 0 modulo p has a solution. We shall see an example to verify the validity of the theorem. We shall take p equal to 13, which is 12 plus 1. So it is of the type 4k plus 1, which means x square plus 1 congruent to 13 should have a solution. And according to the theorem, solution is given by 1 into 2 into p minus 1 by 2. What is p minus 1 by 2 here? It is 6. So solution is 6 factorial. Is it true? 6 factorial is 720. When you divide by 13, answer is 5. So 6 factorial square plus 1 is 25 plus 1, 26, congruent to 0. Result is true. Now see this problem. Find the remainder when 15 factorial is divided by 17. 17 is a prime number. Observe. Using previous Wilson's theorem, you leave 1 and 16, take the product. These p minus 3 by 2 pairs, they will be congruent to 1 according to the method of proof of Wilson's theorem. That means 15 factorial is congruent to 1 modulo 7. So the answer is 1. See another problem on the same line. 2 into 26 factorial. When you divide by 29, what is the remainder? Same method of proof of Wilson's theorem. See 28 factorial, that is less than 29, 1 less than 29. 29 is a prime number, congruent to minus 1. This 28 factorial we will write as 26 factorial 27 into 28. 27 is congruent to minus 2 modulo 29. 28 is congruent to minus 1 modulo 29. Therefore, 26 factorial into 2 is congruent to minus 1. That is 28. Thank you.